حاتني تقرأتي. Yeah, actually, I'm just trying to confuse people. Hi, Tatak. Okay, so greeting is over. Let's go to now. From what we did yesterday, anybody with any burning question from what we did yesterday? So you can raise your hands or maybe in the chat. First, let me share my screen. Where is my screen now? My screen. Okay, share. What is this? Okay. Everybody see my screen? David, can you see my screen?
Yes. Yes,
All
Dr.
right. Okay. Okay, I don't think you need. Florence was saying yesterday she want to look at my face while we are talking, but that will just take up the bandwidth. Any question? Let me see if any question. I got any question. So I will only look at the comment or chat box. What's yes? Okay, yes. So no question. So anything about climate variability, it means you understood it very well. Okay. So let's go to today's thing. What? Where is my thing? I don't want this to be okay. This is a discussion question. We did survey yesterday. Now we go to the another very important area. Okay, so today it's all about climate data, climate information, climate analysis. We didn't do much about the analysis. We just talk. We don't do analysis. We just talk analysis and share a tool that could be useful to you. Okay. So these are my stated objectives for this session. Describe, I mean, okay, you can go through them, but I don't want to read all that, but that is the whole summary of what we plan to do in this specific session about climate data, climate information. Maybe even about climate services, but I think you covered climate services in my colleague, Dr. Hansen's lecture. So here we talk just about climate data, climate information. So I think the first thing is what is data? It's what is information. Normally, I have a discussion in the class about this, what people think data is, what people think information is. But here we just try to define and move on. So data is just numbers. I mean, I think it is just a collection of numbers. It could be temperature data, rainfall data, whatever data in its raw format without any processing. Okay. And usually those numbers, they don't mean anything to people who are not specialists. If you are a meteorologist, you can look at the table of data and say something about it. But if you are not, that data needs to be converted into some useful information. And that information is something analyzed or interpreted data with specific goal. You don't just play with the data. When you analyze data, interpret data, it means you have specific purpose in mind, right? Because maybe it's because you want to understand what the climatology is. Maybe it's because to understand what the variability is. Maybe it's because you want to understand where the trend is, or maybe it's because you want to understand what the risk to crop is. So you have specific purposes when you analyze climate information. So anyway, this the description, the whole description about information. Again, I don't want to go one by one, but I think you got the gist of it. Okay. So where does data come from? I think that's the point. So where does climate data, meteorological data, where does it come from? So it comes from different sources. So I think panel A on the left, it shows you the different sources of climate information. Globally, the most prominent, important actually, I can say, source of climate data is station observation, right? So here you can see station observations. Apart from that, there are what we call balloons, air balloons. So stations are mostly for measuring what happens near the surface. If you want to measure what happens in the atmosphere, there are what we call radiosondes, balloons. So this instrument in here raises with balloon. While it raises, it measures different parameters. Another big, huge source of data is satellite platforms up in the sky. There are a number of them, okay, in different formats. All these different kinds of satellites here, you can see up here. Stationary satellite, we have which are apparently fixed over a given location, or polar orbiting satellites which move around the pole, all of their purposes. So all those observations. Of course, we can also use planes, especially for experimental observations. Buoys, this thing is down here. They are called buoys. They are what we use. Remember, yesterday we were talking about El Niño, La Nina, that we measure. We need to measure surface temperature. There are no stations. It is on the ocean. So there are what we call buoys. This float on the ocean or in given areas. They measure and then transmit data. Those are the buoys, especially buoys for over water bodies. We also use ships that measure different climate variables and then transmit. So all lot of different types of collecting climate data, climate information. Panel B is a typical ground station with different instruments. The one prominent here, what you see is the Stevens screen. This one that hosts the thermometers. So the thermometers, they have to be shaded. Number one, they should be shaded from direct sunlight. They should be shaded from direct wind. So why do we need to do the shading? That's the question for you. Why do we need to shade the thermometers from sunlight and from winds? It's good to think about it. Number two, also the measurement, temperature measurement. What do we call surface temperature measurement? Is not actually surface. It is 2 meters above the ground. Okay, it is what we call surface temperature is actually a 2 meter above the ground, number one. Number two, there will be a big temperature difference between the temperature of the soil and the temperature at 2 meters, actually. And maybe you can tell me why. Let's see. Third question. Anyway, there are other, the wind vane and anemometer, all those of things. And the other one is, of course, what we said, remember, buoys and ships we already talked about. These are satellite constellations. So I don't want to go through the whole thing, but there are so many satellites specifically for weather and environmental observation up there, and they have very good vantage point. One of those satellites actually located over Western Africa, Equator and Western Africa. And it observes the whole of Africa. It's a European satellite, which is called Meteosat. It covers Africa 24/7. I mean, they didn't put it to cover Africa, but they had to put it there for their own purpose and geographical reasons I don't want to go into, but it covers the whole of Africa. So Meteosat, that's where it's come from. Okay. So now this is the types of observations platforms, like I said, all the way the ocean to space. They are all used for meteorological purposes. Okay, we'll come to that. Okay. Number one is source. Number two is what kind of climate data we have. No, what is this thing here? Yeah, okay, so what's the problem? So of course, the main source of the main source of climate data is station observations. So on the right, these yellow dots represent station observations. These are station locations across the globe. But you can see some of them even in the ocean. Some of them, the ones you see on the oceans are small islands, but some of them could be buoys as well. And you can see, like, if you compare Africa to Europe or America, you can see there's a big difference in terms of station network. But for Africa, these are not the only observation stations. These are the stations the African Met Services shared with this global center. Okay, but you can see anyway, still there is a big imbalance because if you see the whole of Sahara area, you don't see many stations. Okay, so the station data is good, is a point observation. It's good for a point. WMO, the World Meteorological Organization, says you need at least a station every 25 kilometers. This is not true in many parts of Africa. I think Europe, that could be true. You can see like it's totally covered. Maybe most of North America as well. People complaining about anything? Okay, I can. David, have a look at the chat and let me know if I need if there anything that needs my attention. Okay, so it is localized. It's very number one, and of course you can see this sparse spatial coverage in some parts of Africa. You can see South America. Of course, the whole of Amazon is a jungle, so you don't expect many stations. So this is station data. Okay. The second one is what we got graded interpolated station data. Somebody the other day asked me, can you interpolate? Yes, you can interpolate. You can interpolate the stations you see above and come up with the data below. This is the graded data. So actually this is from the Globe GPCC, Global James. James, go ahead. What's the question? The point, James, you want to say something? Is there an issue? James Kikonyo, did you raise your hand? Unmute and say something. No? Okay. So the data comes from this image, the gridded data you see comes from GPCC. That stands for Global Precipitation Climatology Center in Darmstadt, Germany. And by the way, you can go there and get the data you want. The data goes back to what? Even I think now they go back to 1901 or even until today. And so it's interpolated data means you get station data, you look above and then regrid them at regular grids every 5 kilometers, 50 kilometers, 100 kilometers, whatever. The one you see, this one, the gridded data you see from GPC is 0.5 degrees. This is the rainfall for January 2010. Okay, this is the rainfall for January 2010, and again, you can get for every and you can see the gridded data covers everywhere. That's the advantage, it covers everywhere. But the question is, let's look at, so GPCC, they can also give you which station they used to generate this product. Okay, here it is. So on the right is the same product, remember? So here is the station they used for the same, for January 2010. So if you look over Africa, and actually many parts of the world, except Western Europe and America, you can see the station. This is supposed to show you how many stations. So you can see in many parts of Africa, it is less than one. It's one or less than one station. It's maybe some in South Africa, I think a little bit. Otherwise, or one or two stations. If you go to Europe, they go. So it's a number of stations per 0.5 degrees, which means what? 50 kilometers. So it's how many stations are within 50 kilometers by 50 kilometers. So in Africa, it's less than one. That goes to this product. You can see in Europe, you can have up to 20 stations or at least 15 stations in that degree. America is mostly what, 3 to 4, 5, 4 stations. So you can see Australia, South America. So for Africa now, but if you see at the product, it looks the same, right? The quality of the product looks the same for you, but for us for let's say Sahara area, the whole Sahel, there are only few stations that are used, but the product looks almost the same as the product for Europe. So for you, if you don't know what goes into this product, it's for you, it's the same quality. But actually, it could be like crap over Sahara and perfect over Europe because of number of stations going into it. So here the point is, you need to know where your data comes from. Okay? For me, I know how to look at which station I used, but for many people, they don't know how to access that information. So they just use the product as if it is a group, because you have data this gives you data every 5 kilometers, no, 50 kilometers. But that doesn't mean that data is good, okay, because of what goes into its station. So this is for a given month, but also you can have climatology also. So this is climatology for January. But here you can see slightly more stations used even in Africa, at least Sub-Saharan Africa, you see a lot of really reasonable West Africa and South Africa, you can see reasonable stations. If you want to look at the climatology instead of specific year, specific month. This is for same thing for what? For January climatology, and this is your July climatology. Okay. Again, I think climatologically, but it's okay. But if individual years, there are issues. So you need to understand the data before you use the data. By the way, this applies to other products that use station to improve the data. Could be satellite data, could be reanalysis, we'll come to later what it is. The global data that use station, you need to understand how many stations go into that product over the area you are interested in. That's very important. That's why I wanted to spend some time on this so that you understand data quality issues. Okay. So the other one is, of course, satellite data. We use a lot of satellite information. What you see here is at the top is CHIRP satellite data over Africa, no, globally. Okay, so again, this covers everywhere. CHIRPs also include station data. Okay, that's so CHIRPs. The last S, the S stands for station. So again, number one, it's satellite. Satellites, they don't measure rainfall. Okay, satellites, they don't measure rainfall. Satellites, they measure some cloud top temperature, cloud top property. Then that is converted into rainfall amount. That's an estimate. An estimate means it involves a lot of error, and the error depends where you are. Number one. Number two, then they want to use satellite to correct some of that error. Again, how much the error is corrected depends how many stations to go into that product. Okay. So satellite. Another one is what we call analysis data. I don't know. This is mainly used by meteorologists. So analysis is it is a forecast product. But it is not called forecast. There is a reason why it's called reanalysis. So it is the forecast combined with observation. Okay, this is, for example, one temperature data reanalysis temperature data. You can see it's global everywhere in the world. Reanalysis gives you I don't know, maybe about 100 climate variables, but it has got its own challenge. Now the question is, so I say reanalysis is a forecast, but not only a forecast. It also includes observation and is a process of combining observation with the forecast is called assimilation, data assimilation, and they assimilate a lot of data. So you have the climate model, you have observation, so you do some analysis algorithm, assimilation algorithm, you come up with the reanalysis. Now, and you can see it says over hundreds of climate variables, a lot of climate variables, but there are a lot of issues. Now, I want to leave you with another question here. So I said, reanalysis is a combination of a forecast and observation, right? So forecast is about the future. Forecast is about the future. Observation is about past. How can you combine the two? How can you combine a forecast, which is about the future, with an observation, which is about the past? So think about it, and that is a question for you. So that's our reanalysis data. We have also what we call the combined data, combined station satellite data. This is one of the things I do for living here. I lead something called not EMACTS, but ENACTS. It's called Enhancing National Climate Services, where we work with national climate services to improve their data. How do we improve their data? We combine their station data, all they have, with satellite data, because the station is good in terms of quality. Satellite is good in terms of coverage. It covers everywhere, but it's not good quality. Station, good quality, but doesn't cover everywhere. So we try to combine those strengths of the two observations. So we combined or blended product, and we do this going back to 1981. So for the countries where we have enacts, they have data from 1981 until today. That's over 40 years of data. So for rainfall, we use satellite. For temperature, we use reanalysis. And temperature, if you want, because the reanalysis goes back to 1961, so you can go back over 50 years for temperature. So we've generated this over 10, 15 countries in Africa. So this is just a table of showing you the strengths and weaknesses of those data I just went through, but I don't want to go through them now, but you can have a look yourself. The other one is, so we looked at data types, but there are also information types, climate information. When it's climate information, it is either about the past, it's historical, right? Well, because you want to analyze trends, extremes, probability of something happening or not happening, you need historical data for that. You want to monitor something, follow something, what happens today, tomorrow, yesterday, right? For early warning, for example. For that, you need real-time observation, current observation. But also you want to know what will happen tomorrow, or next week, next month, the next season, or next year. That's where you use your forecast or projection forecast. And projections later on will come to that in terms of what the difference is. So the data analysis, give me 1 minute. Somebody's at the door, so we'll come. I'm back. So climate data analysis. What is data analysis actually? What do you mean by data analysis? So this is, you remember data versus information? So data analysis is converting raw data into some information. That's it. So you have a data here, what do you see? Right, this data, you can convert into information. And we said when you convert data into information, you need to have specific objective, specific goal in mind. So I can record, convert this data into this kind of information, which is like just monthly rainfall time series to see which years were wet, which years were dry, which years were good or not good. Okay? Same data, or I can convert the same data into another information, like seasonality, which months will have more rainfall. And here you can see this country has July and August being the wettest, and December, January being. So you have this data, the same data, you can convert it into many different information products, or you can even convert it to, I don't know, some box plot data. Again, the same data, depending on what you're looking at. You can maybe convert this into a probability of exceedance or cumulative probability graph, right? Frequency, then into cumulative frequency. Again, different kind of information to say, okay, what is the most likely rainfall for this location? Rainfall amount. So again, same data, different information. Okay. So there are a lot of things you can do with data to convert data into information in time or in space, right? Averaging and time series analysis, anomalies, which talked about, correlation anomalies, or very sophisticated calculations anyway. So pattern even nowadays into AI or all those kind of things. Yeah, so again, this is very important. This is important to keep in mind what type of data was used in the analysis. Remember, I was talking the other day, you can extract grid data and do analysis yourself, but you need to know what is that data is about, where it came from. That is very important. Otherwise, your analysis could be maybe like what's garbage in, garbage out kind of thing. So in terms of data analysis tools, you have, of course, your very popular Excel. You can use Excel. There are I think you have your own tools for climate data analysis. But from the IRI side, this is the tool we have developed, Rija and myself, and I think version 8. This is climate data tool. So it is specifically for climate data analysis. It's free. You can find it on the search for CDT, download and have fun with it. We don't charge you anything. It is a very powerful tool. You can organize your data. Like if you want to download satellite data or analysis data, merge data, do quality control. So generating analysis data means merging the data. If you want to evaluate satellite data, evaluate merged data, do some lot of analysis, visualization. It does a lot of things. By the way, remember on the first day I mentioned the curriculum for universities, climate risk management in agriculture for universities. CDT is part of that training. It's part of that curriculum. And it's initially we didn't mean to make it part of the curriculum, but when we introduced it to university professors, they loved it. We gave them a training, I don't know, 1 day introduction. It was not enough, but then we had to do what, 3 day or whatever, remote training or for them on CDT. So it has become very powerful tools. So for us, we do quality control, for example. This is done using it. So this is what an output from CDT. So here is time series of temperature. Black is good, red is bad data. Okay, I don't know. And this is what, remember, this merging, this is done by using CDT. And CDT, initially, uh, CDT was developed specifically for national meat services. Okay, so this is actually somebody from Ghana the other day in the training said, because it is targeting national meat services. And the lady used CDT, climate data tool, and she changed the name CDT to something else. She says CDT is what it is. What did she say? She said that it is the can-do tool. It is the can-do tool, which means it does a lot of things. CDT. That's about national meat services. But last September, a year ago, we asked people to register whenever they download CDT or when they upgrade their thing. We asked them to register. And we were very surprised to see where CDT is being used. Places we even never thought they would. Remember, this was mainly for Africa, national meat services, and a couple of countries were in South America. Like you see the gray colors, these gray colors here. That's where we went, where we installed CDT and trained people. But the other is just happened by the we never went to Australia or Europe to train people on CDT. Now you can see how many people are using it, and many of them are actually from universities. Urel, you want to say? Okay, maybe we come to something later. So this is about CDT. This is for you to analyze your data. If you have the data, organize it, analyze it, do a lot of fun with it. And these are the numbers you see here are how many people downloaded the tool. And you can see the maximum number of people are from Ethiopia. Over 200 people downloaded CDT over the last 1 year. I mean, maybe before that, many people might have downloaded, we don't know. But over the last 1 year, over 200 people from Ethiopia. I think 64 in West Africa. That must be Ghana. Kenya also, we do the number, but actually the big number in Kenya because that's where we were, like Ghana, Kenya, Ethiopia, Rwanda. We've been, that's the places. But this where you see 1111 is like somebody from somewhere randomly downloading it. We have never heard of those people. Even so yeah, South America, for example, you see 14. I think we've been there. The 8, 6 others, we've never seen them. Anyway, just to tell you, just to encourage you, have a look and have fun with it. Okay. The other one, if you are very lazy or too lazy to analyze your own data, then you can have analyzed data. But this is what we call map rooms. Okay, this is an interactive online map room, but this is limited to those countries who which have implemented Enact. So I will show you tomorrow. Because today I don't think we have time for today, but I will try to show you tomorrow some of these map rooms. Some of them work, some of them may not, but they have got a lot of information, an amazing amount of information already analyzed. You just click around and download what you want. Not the data, but the product, okay? The map rooms. So now it is time for you to ask your questions.
There are some questions you can click on Q&A and respond to them.
Okay, let me see. Q and where is my Q&A thing? You can also raise your hand. Okay. But I don't see anything here. This one?
When you click Q&A, there are a number of them.
I can see. Emmanuel is, if satellite data is estimated data, what could be the reason for the level of accuracy? Who said satellite data is accurate, Emmanuel? It's an estimate. So an estimate means it has some information in it, but I never said it's accurate. That's the reason we are combining station data with satellite data. I mean, satellite data with station data is to improve its accuracy. But I mean, in Europe, it is more accurate than in what? Europe than Africa? I don't think so. Actually, in some cases, satellite rainfall estimate is better in Africa than in Europe, unless you are talking about radar or something else. Satellite itself, actually, in many cases, it's better over Africa than over Europe because of the type of the climate. Anonymous attendee who doesn't want to share his real name says, in African context, how to integrate application of climatological data with other agricultural. Oh, that's a good question. How do you combine climate data in agriculture? I mean, CDC, you can do some of that. You can do like regression, la, la, la. But for that, you need your own other tools. Okay, because CDC can help you to, like, so for example, extract data for a given location and the time. So you can take that data to Excel or to other to process the data. So yeah, I mean, from Charles, I will say CDT, but you can also find other data in terms of what tools are effective for the climate data analysis. So Malawi, two things. In Malawi, Malawi is one of the inactive countries. So it's an inactive country means the people from the National Met Service have been trained on CDT. So they know, so you can check with them. Not only that, in November, this coming November, Rija, who is the main developer of CDT, will be going to Malawi for a refresher training. So if you want to be part of that, contact Malawi Met. Okay. Mozambique, we've been hoping to do Inaxis in Mozambique, but we have not had a chance, so don't know. Okay. It's easy to get the data for free for the students. Which data? I mean, Inaxis data in many countries is free. You can ask them. It's not online, but you can ask them. Deraj says, is it possible to get daily data and temperature data from INAT? Yes, of course, but the data belongs to the National Met Service. So if you go to it, you can ask the Ethiopian Met Service for the data. They can. I think Ethiopia, the National Met Service, EMI now, Ethiopian Met Institute, they've been giving away data to university students for the last, I don't know how many years. Okay. Alex, university, how can artificial intelligence and machine learning assist? I mean, so the one thing about machine learning or AI is they are very data intensive. Okay, so if you don't have the data, the best AI wouldn't do anything for you. I think for me, actually, I'm worried that Africa might be left behind in this AI revolution because of how much data we have. Be it climate, agriculture, for example. How much yield data do you have for each country? How organized is it? So for me, we need to make more efforts, number one, to organize our data, and number two, to make it available to people so that they can play with the data using AI or machine learning. Okay, so again, AIs, they learn from the data. Machine learning means they're learning from the data. So number one, you have to have the data. That's not enough. You have to have good data. If you train your what a machine learning algorithm or AI algorithm with bad data, then it is learning something bad, no? Okay, all about it. Anonymous. I think I passed this one. There is some difficulty in CDT. Well, there's instructions. So if you go to the CDT GitHub, especially for Windows, very easy. to install it. It is a little bit hard for Mac, but that's my problem. Can extract regional average data for CD? Yes, of course, Gazan. You can extract data for Warada, zone, region, box, a lot of things. Amdom Sam, can you tell us about the data analysis tool? Pattern, what? Pattern recognition, not like AI. I already told you about AI, right? But no. Gazan, can I extract zonal average data? Of course, yes. Anything else? Oh, what about do we have anything in the Q&A side of things? Anybody want to raise your hand? So let me check. Two?
Is a raised hand from Uriel. Uriel. And then Uriel. You
Okay,
can
maybe
unmute
by
and ask
accident,
a question. Maybe they are not.
went home, maybe.
Okay.
Okay.
You can also check in the chat. There are some questions in the chat.
Yeah, that's what I've been looking at here. Wow. Tad Access, thank you for your informative presentation. I have a question regarding the use of CDT. CDT is indeed a powerful tool. Wow, thank you for climate data analysis. However, says Tatak, I am encountering an issue when trying to export raster data downloaded from chips for visualization ArcGIS. Is there a specific mechanism? I mean, this is more technical question, so I cannot answer them. More technical question. You can reach out to Rija, a technical person. Like this specific kind of thing, I cannot answer that. Here, I'll answer more general. Okay, anything? Okay, I think that is all I see here in terms of any other questions. If not, maybe it's good to talk about these questions. I mean, I don't want to, don't have time to go through it now. So have you ever used climate or weather data in your work? If so, what type of, and what would, I mean, this is for classroom discussions. So you can have a look at them. Immediate question, are there ways in which the issue of data poverty, which means insufficient historical climate records in some regions, inhibits your work, which means does the fact that data is not around or available affect your work? The next one is is a good question. How might climate services generate information in regions experiencing data poverty given what's currently available? I think this is a good question. If you maybe you can answer because we already talked about this one. Okay. And the next one is what precautions does one need to take while using what? So it means in other words, if you want to station data, what do you need to be aware? Interpolated data, I already said a lot. What do you need to be aware? Satellite data, what do you need to be aware? I already said analysis model data, what do you need to be aware? Because if you're using any of this data, I'm hoping you have got a couple of things in terms of what you need to be careful about, what you need to be looking about. Any questions or what? So Maaza says, can we access CDT individually? Of course, yes, Maaza, it is free. You can just download. You can search for CDT now, download it, and I don't know, start using it this afternoon. But you need data. You have to have your, but any sometimes you can even use CDT without your data because you can download satellite data, you can download analysis data, but it's always good to have your data. CDT is a free, I said again, it's a free tool. Sorry about the network blessing. Which climate model is the most relevant to Ethiopia? I have no idea. Okay, good question from Kia. Is there a tutorial video for CDT? I mean, we started it, but then because CDT keeps on changing, we keep on updating it. We don't have a very good official. I think that's a good point. We are planning to do that now. I think it's more or less stable on CDT version 8 now. So we will, yeah, it's a good point. We will start maybe developing some videos. But there is a manual. There is a CDT manual. Again, needs to be updated, but there's CDT manual that explains each step. Agnes, yes, I have used weather data during my master study to correlate the, okay. The difference between rain distribution and, so when you say rainfall distribution, it could be temporal distribution, it could be spatial distribution, right? So it could, by the way, it could be rain distribution. When you say rain distribution, rainfall distribution, I'm assuming the rainfall amount. There is the rainfall amount across space or across time. And it can also be the distribution of rainy days. It could be the distribution of dry spells. It could be the distribution of wet spells. So there is no distinct saying, okay, this is what we mean by rainfall distribution. Can we do shift without validation? Can we do without validation? I mean, but you don't have to do validation yourself, but you should look for papers, publications that talk about that product, how good or bad it is. You are not expected to do validate every satellite product. That's not your area of work. Now, in terms of what CDT performance, Sentayo, download it and look at it. There are so many things it does. It doesn't take to install it very long. Anyway. Okay, so last 4 minutes we are left. Francis is teaching soil chemistry. So he was late because he was teaching soil chemistry. So anybody got any good question about soil chemistry, you can ask Francis. Okay. David, now can we do our usual survey? We have 3 minutes before break, and if you can do that, it will be great.
Okay, so we are going to launch it.
So, like I said yesterday, we are doing this for each session to see. So, by the way, do you have the report or from yesterday, David, or? Well, I didn't save anything.
Yes, it is saved in the system.
Okay. So good. For me, it's really good to compare which session is difficult, easy, understandable. That's why I want to do that. So that, because if you ask them about everything, then you wouldn't know which one to improve or to review. In the meantime, while clicking the thing, you can also ask questions. So first question, how clear and easy to follow the presentation is more about the presentation itself. Okay. Number two, how would you rate the difficulty about the content? And number three, were you able to understand me? Okay. Neutral? What does neutral mean? I don't care whether I understand it or not. How clear and easy to follow the presentation? What? How many people do we have here? Not 200. Neutral? So neutral means I don't care, or comme si comme ça. Who's anybody from West Africa? Comme si comme ça. Est-ce qu'il y a quelqu'un qui parle français? Non? I want to brag about speaking French. Okay. So we have a lot. We have Ojo saying Nigeria. Okay, somebody says yes. Yes. Oh, Senegal. Bonsoir, Senegal. We do a lot of work in Senegal. So we work with Senegal May Service. Agnes, Cameroon, ça va? I've never been to Cameroon, and we want to do Enactus in Cameroon. Yeah, ok, DRC. Comment ça marche là-bas? Côte d'Ivoire. Ça va, tout le monde? Ok, Ghana. Bénin. Ok, Moray from Bénin. Ça va? Rahel what? Rahel, you speak French? Yeah, you're down? Niger, bien sûr. Burkina, bien sûr. Ça va parfaitement. What's that? To say. How do you pronounce Toussaint? Mali. Yeah, we have been to Mali, to Bamako a couple of times. We have Enactus. Of course, Uganda is not Francophone, Julius. Oh, Sudan. Assalamu alaikum. So, okay. Are we done with okay, I think we are done. We got what? People don't know. So we got what? 63% participation? The rest people, maybe they are not there. Okay. So now it's our break time. So we should be back at 15 past the hour. And in the meantime, I can play this video. Which one is it? About ENSO, I think. For people who didn't understand ENSO well yesterday, I had a couple of people complaining. So let me play this YouTube video for you.
Every now and then, you hear something about El Nino, or less often and notoriously, La Nina. Maybe you've heard it has something to do with hot water in the Pacific, or was it cold water? Either way, it sounds kind of important. So what is it? The ocean is responsible for just about all of Earth's climate. Changes in the ocean always coincide with a change in the climate. The larger the change, the greater the impact. Not only is the ocean responsible for Europe's mild winter climate, but it can also have visible effects. Notice any similarities between these continents? There's a desert on the western coast for each one. This isn't a coincidence. This is due to ocean currents depositing colder water at these shorelines. These colder waters mean less moisture in the air and thus a drier climate. Since an ocean's temperature is essential in dictating the climate nearby, it should come as no surprise that if El Nino is a change in ocean temperature, it should have an impact on climate. Let's figure out why. The first thing to comprehend is the basic principles of fluids. Despite fluid dynamics being an extremely computationally intensive area of mathematics, it still follows two simple rules as long as the fluid isn't bounded by a container. One, hotter fluids are less dense or have a lower pressure. And two, fluids move from high pressure to low pressure. So if you change the temperature somewhere in a fluid system, you'll completely change the flow or behavior of that fluid. In large bodies of water, like lakes and the ocean, the top layers are constantly warmed by the sun. This warmth penetrates a specific depth, so we can expect all water in this region to more or less maintain a constant temperature with slight variations with depth and the amount of sun. This means any water below this line will probably be cooler or denser than the water above it, and thus can't properly rise to mix and absorb its warmth. This separation compounds, and you get a very noticeable delineation between warmer water and cooler water. This is called the thermocline. The thermocline is the most important factor in regards to El Nino. Keep that in mind. Let's look at how the Pacific Ocean normally behaves. We have colder water over here, which cools the air and thus increases the atmospheric pressure. We have warmer water over here, which warms the air and creates low atmospheric pressure. As one would expect, the air flows from high to low pressure. Normally, there should be no reason for this temperature imbalance. But since the thermocline is important, that probably has an impact. The wind caused by this difference in pressure tugs on the ocean via friction, creating surface currents. As the water displaces to the west, it needs to be replaced, so water from below rises to do so. Here's where our thermocline comes into play. The thermocline in the east is very shallow, less than 50 meters deep. The surface currents created by the wind affect roughly the top 50 meters of water. That means the water that rises to replace it comes from below the thermocline. That is to say, it's very cold. This keeps our surface temperature cold and keeps our pressure gradient and subsequently the wind strong and active. Because the water generally always moves westward and pools up there, the western thermocline is very deep, causing the surface temperature there to remain warm. So as long as the eastern waters stay cold, things progress normally. El Nino, therefore, is the phenomenon of the eastern Pacific failing to remain cool. But what we have here is a positive feedback loop. Sure, El Nino is the warming of the eastern, but why does this happen? What breaks this positive feedback loop? What I'm about to present could change in 50 years as computers improve, because despite fluids being very simple, calculating and modeling them accurately is very difficult, and it gets exponentially harder as the scale increases. So when talking about the scale of the Pacific, yeah, it's kind of hard to be sure our models are accurate. But what do we think is happening? Earlier, I mentioned there's no reason for the West to be warmer than the East. Both points are along the equator and receive the same amount of light. So how does this imbalance occur? Any fluid on a rotating sphere, like Earth, is affected by the sphere's rotation. This manifests in lateral motions we call Rossby waves. If we imagine a distribution of particles along a single longitude of Earth, we can compare their relative rotation in space compared to the rotation along the normal axis. On the equator, 100% of the rotation is on the y-axis and none along the normal. Whereas in the poles, 100% of the rotation is along the normal. If we compare the relative rotation along the normal axes, we can see that water particles rotate faster as they move away from the equator. What's this mean? Well, any water that moves slightly away from the equator will encounter faster rotating water particles that will push them to the west, opposite as one would expect from the Coriolis force. This push to the west creates our Rossby waves, and thus we get the start of how our Pacific should look. As this water travels west, it starts building up and pushing down the thermocline, which is a criteria needed to keep the Western Pacific warm. These arriving Rossby waves also reflect off the western coast and begin their journey back east as what we call a Kelvin wave. But the Kelvin wave is of lesser impact than the Rossby waves, as the Rossby waves are soon reinforced by easterly wind flows. Rossby and Kelvin waves can be detected at the ocean surface, but they are only roughly 10 centimeters in height. However, in the thermocline, these waves can cause fluctuations of up to 100 meters. Huge variations in thermocline depth. Now we've reached the disputed part of our El Nino. What causes the tipping point? We've seen how Rossby waves can create warm water buildup in the west, which pushes down the thermocline, keeping the water warm. This warmth creates a low pressure region, which causes winds to blow from east to west. This wind brings more water and also helps amplify the cool surface water in the east, thus continuing the cycle. So how do we break this positive feedback loop? There are two main theories. The first is that there is a natural oscillation between buildup of warm water in the west, followed by reflection of waves to the east. This reflection then pushes down the thermocline as it goes and warms the ocean's surface. This oscillation can be affected by noise or interactions with the atmosphere. There's also a more stable yet stochastic model which suggests that this buildup of warm water in the west is a stable state as long as the winds and currents holding it there are maintained. But of course, nature isn't constant, and eventually there will be some disruption in wind flow and currents, or slip, as I like to visualize it. This slip causes the warm water volume to destabilize and discharge from the Western Pacific. There's decent correlation between strong westerly wind events and the initiation of Nino events. These strong winds push the warm water east, starting the discharge. The produced Kelvin waves then flow to the east, lowering the thermocline as they travel, while subsequently raising the thermocline in the west. This model is a bit more attractive as it can explain how or why Nino events have different timings and variabilities in strengths. But both models look rather similar, and perhaps they are one and the same. Only stronger computing power may tell us for sure. Because of the redistribution of the warm water and change in the equatorial thermocline, we have a reversal in ocean temperatures, warmer in the east, cooler in the west. And since ocean temperatures affect climate, we see drastic changes in the climate in the east and west. As this warm water reaches the east, it collides with the American coast, dispersing to the north and the south. These changes in temperature affect not only ocean currents, but atmospheric currents too. We aren't quite sure how and to what extent it does, but someday we may be able to explain how exactly El Nino causes climate impacts all over the globe. After an El Nino event, the warm water content in the equatorial Pacific is drained, and thus the process starts over. Lastly, as a quick addendum, I should mention that the scientific community has agreed on the existence of two Nino events. Those in the east, like we are familiar with, and those that occur over the middle of the Pacific and are further from human observation. The mechanisms and atmospheric interactions are basically the same, but it appears that their occurrence is becoming more common as sea temperatures rise. It's still not quite certain how this will play into global weather patterns in the future, but it's certainly something of interest to keep an eye on. And that's hopefully a good explanation of what causes an El Nino event.
Okay, hopefully everybody's back. Hello again. By the way, for the Ethiopian brothers and sisters, happy Mescal Day. እንኳን አደረሳችሁ. I think today is what the first Mescal celebration. Mescal in Ethiopia is a Christian outdoor big celebration. I think something to do with the finding of the true crosses. Ethiopians think they have the true cross and they found it some time ago. Okay. What do we have here? Okay. Okay, yeah, but we're linking it down. See a lot of people who want to go out and burn campfire kind of thing. La, la, la. ሙዑዝ ገብሩ ሙዑዝ እና ሙዓዝ የተለያየ ነገር አለ ዲፍረንት Mahilet David, yes, okay. I can see a lot of reaction from the Ethiopian crowd. Nardos. What, Margaret is also celebrating Mescal? Okay, let's do forecast. Okay. For today. By the way, we are almost done. So tomorrow we will be spending some time on the climate change, and then maybe we'll show you some of the map rooms. Maybe the first half tomorrow we'll spend on climate change, and maybe second half we'll show you some of the map rooms, and maybe we can finish early. We'll see how it goes for tomorrow. So let's go to weather forecasting, climate forecasting, maybe climate projection, we'll see later on. All right. Okay. These are our objectives for this session. Okay, so let's get into it. So we have forecast at different time scales. So you see, we say weather forecast, climate prediction, climate projections. So which this happen at different time scales, from an hour all the way maybe to a century, right? So what we call weather forecast is mostly up to 10 days. That's called a weather forecast. We have nowadays what we call subseasonal forecast, almost from 2 weeks, a month to 3 months. Seasonal, mostly nowadays 3-4 months, but it can also go up to a year. There is what we call decadal prediction. So weather is forecasting, maybe seasonal, subseasonal, after that predictions. So interdecadal or decadal prediction, what will happen in the next 1 year, 5 years, 10 years. And of course, your multi-year or decade scale, that is called projection, actually, not forecasting, not prediction, but projection, because they are different things. Okay, from weather forecasting all the way to climate projections, different times. WMO, they have their own definition of the different time scales. So from now to a couple of hours, they call it nowcasting. Then what they call very short range, like up to 12 hours. Then short range forecasting from 1 day, from 6 hours, 12 hours until 3 days. Medium range, extended range, okay? And then this long range forecast. So now long range is like the subseasonal, seasonal kind of thing. And then all the way to climate forecasting, like this is WMO's version of classifying the different time scales. So this is more general, this is more specific to the World Meteorological Organization, which is the global authority on meteorology. Okay. So in terms of how do we predict the different time scales? So for daily, like days, if you're forecasting in days, that the weather time scale, that the information for the prediction or for the forecast, actually, for the weather, comes from current observation. So you observe yesterday and today, and then use that information to forecast the future tomorrow, the day after tomorrow. Once you go into subseasonal and seasonal, it depends on sea surface temperature. That's where El Nino, La Nina phenomenon comes in. If you want to look into years ahead, now instead of now you see subsurface, which means under the water. Under the subsurface means under the surface. You look deeper into the ocean temperatures, and that's part of it. Part of the information comes from there. Decades means your climate change projection. Actually, that one has nothing to do with what you observe. Projection has nothing to do with what you observe. It's only about atmospheric composition. What will be atmospheric composition in 20 years, 50 years, 100 years. That is what climate change projection is based on. We'll come to that later. Okay. So in terms of weather and climate forecast, there are uncertainties associated with the forecast, be it daily weather forecast or climate predictions. And uncertainty means error, by the way. It is just a fancy, uncertainty is a fancy word for error, forecast error, prediction error. So this guy, this is just a cartoon. He wants to play, if you want to play dart. So how good you might hit the center of the board depends partly how far you are. Okay, but it all depends how good you are, but also how far you are and what happens in between. So a lot of factors. If you are closer, you are good. You see? Okay. So if you are very close to the board, okay, so your error is small. So which means forecasting tomorrow, the day after tomorrow is easier. So weather forecasts are normally more accurate. Not in Africa, but in the West, Europe, America, Northern Hemisphere, or Southern Hemisphere for that matter. Weather forecast is very good. They can tell you it's snowing tomorrow, it will snow tomorrow. In Africa, weather forecast is okay, but it's not as good as Europe. It's the nature of the climate. Okay. For seasonal forecast, you can see now, because it's far away in time, or for this case, so now you see the error or uncertainty increasing, seasonal forecast. For seasonal forecast, actually, Africa is better than Europe. Again, because of the nature of this La Nina, El Nino. Mostly, seasonal forecast is not always, but mostly better in the tropics. And of course, if you go to your climate change projection, that anything can happen. So again, this showing you the uncertainty at different time, or time, whatever, time lags or time scales. Okay. The further away in time you want to predict, the the larger the error. That's what is this saying. So what's the weather forecast? So it is starting. This is what, for example, this is what you see on TV every day. That's the weather forecast. What you see on your app every day to see what's happening outside, that's the weather forecast. So this is just an example of weather forecast. Like I said earlier, it depends on initial condition, what's happening now, then from that data. So it will tell you how today's weather evolves tomorrow, the day after tomorrow, until a number of days. So there are two sources of errors. You see, again, uncertainty means error. Number one, when we say starting from today, which means we have a good understanding of today. Having a good understanding means having good observation. So if you don't have a good observation to start with, then the uncertainty in weather forecast will increase. But another thing is also how the system is evolving. Sometimes it might evolve in totally different direction than you expected. So in terms of how the forecast is presented, there are different ways of presenting the forecast. We will come to some of these later. So the deterministic forecast is this one. See here, the forecast is 68 degrees. So this is deterministic forecast, 75 degrees or whatever, minimum, maximum degree. This is deterministic. Probabilistic means this is probabilistic. You see, the temperature is deterministic, it tells you the amount, but the rainfall is probabilistic because it tells you that the chance of having rainfall. So on this day, it is 24, there is 25%, 24% chance. On this day, it's 80% chance. So this is probability. Okay, this is deterministic because it's not the probability of having temperature. This is actually the what temperature you should expect. So deterministic, probabilistic. Again, we will come to probabilistic later on. Interval is like, okay, it will be between this and this. Category is to say it will fall within this category of hurricane, cyclones. If you know, they have categories, category 1, 2, 3, 4, that kind of. So now talking about, that was weather, now talking about climate predictions. This prediction of weather-related variables into the future, right? It's more than about 2 weeks. Aims to make broader, this is very important, aims to make broader, more general predictive statement of the characteristics of the atmospheric condition. So it's about telling you would next season be normal, above normal, below normal, okay, that kind of. Focus on more larger drivers of long-term atmospheric behavior, so like surface temperature, El Nino, La Nina, that kind. But it will provide very good, not very accurate, but helpful insight into the next season might look like. Okay. So again, the rationale, we have seen this figure before, and the reason I'm bringing it is the fact that some of the seasonal forecasts, not most of the time, seasonal forecast depends on the outlook for El Niño or La Nina. Remember, before they forecast what the season might look like, what the rain in the season might look like, they first have to forecast what the El Nino will look like. And IRI, my institution, the International Institute for Climate Society, was the first that started forecasting El Nino in 1987. Okay. Actually, at that time, when IRI was established, it was called International Research Institute for Climate Prediction, because we started El Nino forecasting. Of course, now it's being done by others as well. So there are a couple of methods. The main ones are, one is statistical method. I don't want to go through this one. This is just having a regression, let's say, between El Nino index and rainfall over Addis, over Nairobi, or Dakar. Okay. So again, this is where those El Nino parameters are measured. The other one is dynamic. This is based on physics and very complicated mathematical models, which these models are called general circulation models. So these models try to describe what the atmosphere, the whole Earth climate system, land, ocean, atmosphere, how they behave. So, by the way, a model is a replica. It's not a replica. It's a model means it's more of a caricature, right? So there's no way you can capture the whole actual atmosphere. So modeling means you try to simplify the whole complex system, but still using so many. It involves all understanding all this system from land, ocean, the atmosphere, and the different activities. And for that, you do use a lot of mathematics and a lot of relationships to come up with the model, the general circulation model. And these models are run globally. So here that's to show you the Earth is, the globe is divided into grid squares across the globe. Depends how big the circle is, or it depends the resolution of those. Initially, when they started, they were about 250 kilometers by 250 kilometers, but today I think they're down to 25 even kilometers. I think not. So you have to do each grid around the world, but also up into the atmosphere. I think up to 18, 20 kilometers into the atmosphere. So to run one day, or they do this like every 10 minutes, 15 minutes for each grid. And it takes forever. It requires a really, really powerful computer to perform this kind of forecast, even 1 day, 2 days, 3 days, kind of thing. That's why I think there's no center in Africa doing this kind of thing. South Africa, I don't think so. There are only very few global centers doing this kind of forecast because it requires very powerful computer. I mean, all that kind of thing. So there are what we call global producing centers, and many others create the data from this. So European model, American model, Chinese, Canadian, I think Australia as well. But again, limited centers because of the computation it involves. Okay. Okay. So for this, the source of error, the scale, if you are doing 250 kilometer by 250 kilometer grid, in that 250 by 250, you can have mountain, lake, valley, whatever. So you are smoothing out. So in a sense, you are smoothing out the local factor we looked at. So that will affect how good the forecast is. But also again, a model is an assumption. So that assumption is also as good as how you know about the atmosphere, or also how much data you have. So there are different sources of errors for this model outputs. Now, another thing to understand, this is very specific to seasonal forecast. So let us remember we talked about climatology. So we want to forecast the next season. So in the dotted box, this is, let's say, let us do Accra. Okay, this is, let's say, rainfall for Accra. I have rainfall for Accra over the last 30 years, different amounts, right? So for a given season. So if the lower rainfall amount is here and the highest is here, so the rainfall amount from Accra will fall somewhere in here. somewhere in this dotted line. Okay. And if I know exactly how much next season will be in the X amount, next season, the rainfall amount will be X millimeters, that's deterministic, right? They say, I know exactly how much, all right. But seasonal forecast is never deterministic. So which means your forecast can happen anywhere. Right? So it is your analysis when you provide your forecast, right? In the forecast can fall within the climatology, within what happens in Accra, but it could be either low as down here or as high as up here. Okay, so this is the uncertainty error in terms of, that's why I will come later, we say above normal, below normal. Now, assuming the rainfall is, let's say, 100 millimeters down here, the minimum, and up here is 1,000 millimeters. So in between, the rainfall will increase upwards and decrease downward rainfall amount, right? So we can divide this thing into three categories, right? The lower one, the middle one, and the upper one. So the lower one, low values, the middle one, middle values, the upper one, higher values. So this is our forecast anyway, that's what is covered. But now we have a threshold here, threshold 1, threshold 2. Normally, this is like 33%, 66 percentile, and then above. So this is between 33 and 66 percentile, right? So anything below this is below the 33 percentile, lower rainfall values, medium rainfall, higher rainfall values. So if you look at your forecast, could be in any of our current forecast, we said it could be somewhere in here. So the probability of being in the low value, in the low, you can count here. The probability of being in the middle, you can count here. And if you look at this figure, this forecast, so these are the probabilities. So for this forecast, which probability is high? Is P1, P2, or P3? I mean, you can see P1, only one line going to the high level. P2, number of lines going there. And P3 again. So in forecast, you get from the Met department. So when they say it is below normal, next season is below normal, they are talking about the lower category, which means the rainfall amount will be anything in that lower category. When they say it is normal, they mean rainfall will be in the middle category. So above normal is not above a given value. You have to, that is the need to understand, by the way, many people don't understand. When they say above normal, it's not above one value. When they say normal, above normal means it will be in all these categories. It could be any value in this category. Normal, below normal. Sometimes they even say normal to above normal, or normal to below normal, which is very confusing. So which means normal to below normal means P2 and P3 combined, which means the value could be anything here. Okay. Just for you to, that's very important to understand if you want to interpret seasonal forecast by National Climate Services. This is the same thing. It's more statistical to say how do we divide those into three. That's why this is called terciles. You can see terciles, because we divide the whole data, the whole observation of that 30 whatever years into three categories: 33%, 33, and 33%. Okay. So normally your data is equal, right? I mean, here from the actual observation, the number of data here, the same as number of data here, from climatology observation, of course, by the forecast. So this is what it means. Each category has 30% of the data from the total data. But when we give a forecast, so if the Met department gives you the same probability here, below normal, above normal, if they give you the same probability, they're not giving you any information because that is what you expect anyway. So in forecast, they give you the shift. In this case, this is your what expected climatologically, but here is the forecast. So you can see the forecast shifting towards the right, towards more the above normal side. That kind of. It says higher probability of above normal rainfall. So here, for example, is what forecast from the SALIC climate centers from Sarkov. So above normal, normal, and below normal. So different colors tell you above normal, normal, normal. You observe here, for example, the whole blue area here. They say there is 35% chance of being above normal, 40% below normal, and 25% below normal. And remember when I said, so if it is 33%, then it's climatology. Actually, you don't need the main service for that one. So how good the forecast, actually not how good the forecast, how the information value depends on how these numbers are written. For me, or for you, we want to know if it is, if these numbers are like 80% or 90%. Because if you know, I don't know, actually I want 100%, right? Instead of for this 35, I say above normal is 100, the others are 0. That's the forecast I want. Because I know it will be above normal. That's not possible at all. But okay, at least maybe 70% here and lower values here, or the vice versa. So the how good the information depends how different. Normally they don't go above 60% for a given category. But I think last year, I think from ICPAC, I saw 80-something%, which means they're very confident at that category. And here you see how they use the colors also. So this is not good. They say above normal to normal. Remember I told you above normal to normal means, above normal to normal means this is the whole category here. So here, actually the weights present is not good. Normal to, instead of just telling you above normal, normal, anyway, this has a lot of issues. I don't want to go through that, but of course, here is the one from IRI, actually. A little bit different, presented differently. So for October, November, December, coming this season, issued in September. So here you can see the categories. Brown is below normal, or whatever. This is below normal probabilities, above normal probabilities, normal probabilities. When it is white, it means either not rainy season or so. For the coming season, October, November, December, IRI expects these areas to receive above normal, which 50, even you see the blue one, 60% probability. This is very good, 50 to 60% probability. Here you can say this area here, saying about 50%. Probability will be below normal. Up here, yeah, 60-70% below normal. This pink area, it means it's normally dry, so it doesn't have rainfall area. And so when the white are like normal or rain or kind of thing. So anyway, this is a forecast, and you can you can compare this to this slightly better, but not. This is for temperature. The same thing from IRI. I don't want to go through it again because we have seen the rainfall now. There is another one, another form of presentation, what we call flexible presentation, flexible forecast. In this case, this is again part of the Enactus approach. In this case, you decide your threshold. The user decides threshold, and you say, okay, what is the probability? I don't know. If your corn requires 300 millimeter a season, then you can say, okay, what's the probability the next season rainfall will be above 300? Then it will give you the probability. Or you can click any location in the country. Here is Kenya. It gives you the forecast in red and the climatology, the normal, in the blue. Here as well. So, I mean, I don't want to go through this, but they give you just like what's the probability above having about 200 millimeter, 400 millimeter, 600. So for Kenya, for this location in Kenya down here, probability of having above, let's say, 500 millimeters is 0. So it's mostly under 500. And you can say the probability for 200 millimeter above for the climatology is about what? 30%. But for the forecast, it's almost about 50%. So here the forecast is shifting towards the right, which means towards above normal. Again, I don't want to go in detail. If we have time, we can go through the whole process explaining it. This is another training by itself. So why probability forecast? I think because number one, we are not certain, and probability will just tell you how likely that might be. That's why it's better, because we are not sure, by the way. We are giving you probability because we are not sure. If we were sure, it will be deterministic. It will tell you, okay, it might be 600 millimeters, but instead, we'll give you the probability it will be in or outside of a given threshold. The issues with using the forecast, of course, science still limited. We are not there yet. How the forecast presented, we have seen that. And again, even if you get the forecast, what do you do about it? Well, we saw how systems climate is, but communication, how the information is communicated. I just showed you what means normal, above normal, below normal, but many people didn't know. Even some meteorology staff, they don't understand what normal, above normal, below normal means in some cases. Now, climate projections. Okay, maybe I put it in the climate change section tomorrow, but anyway, it's not a big deal. Any question now? Any question on this side? Question about climate, weather forecasting, climate prediction. I will look at the comment section only. Please don't. What? Is it? Okay. Oh, this is from the morning. Okay. La, la, la. Any questions? Either raise. So, David, help me with anybody raising their hand. Let me so.
No, I think the people have been typing on Q&A and in the chat.
What time is it now? Oh, okay. Thank you. Okay, that's answering the question. Yeah, we will share all the slides. Sir Knight is asking for audio recording. Let's see anything on the Queen side of things. Oh, okay. So David just shared the recording link. Recording link. Where's my? I want to put it here. Okay, let's go back to the questions. Can you tell us about the data analysis tool? What? CDT? No, this is from the morning. This is the morning, so I don't have anything here. No question, no question. Thank you, you are welcome. Now, what was the criteria for category forecast as deterministic? I don't understand the question, that one. No. Felix says, thank you, useful insight into climate change. We have not talked about climate change, actually. We'll talk about climate change tomorrow. Okay. People waiting for the slide. Innocent says this. Oh, the insight was great. Thanks. Thank you. You're welcome. You're welcome. So Rahel asks why short range is better in Europe. Because in Europe, we have what we call a frontal system. It's the system. When we say system, it's like cloud, moisture, what we call air mass system that moves slowly. But from west to east, from westerly, from westerly means from the west. So because it is slow moving system, it's easy to predict where it will be tomorrow. If you know where it is today, and you know how fast weather is moving, you can tell where it is tomorrow. So in simple, while in Africa, I don't know, in Ethiopia, in Addis, it can rain in Kazanchis and may not rain in Piazza because it is convection. The convection can pop up anywhere. So I think that's the main thing without going into the details. So Abebe says, what is the normal? Like the normal, like I say, the normal is depends on the historical data you have. So the national method for Addis, they take 30 years of data, rank the data, divide into three. So the middle three is normal, the below is below normal, above that above normal. So normal is not one single value. Normally the range of values. I showed you, Mohammed, the forecast for next season from the IRI side. What is it? This is the forecast, remember? From IRI. ECPAC, they have their own forecast. IRI, this is the forecast for October, November, December 2024. Okay? These are the probabilities. Above normal probabilities, below normal. So they give you in one figure. It's not just category, it's pixel level. So I think it is a good information. Is ocean volcanoes have contribution to El Nino? No. I mean, volcanoes, they have impact on the climate, but I don't think on the El Nino. I'm not sure, but I don't think so. Okay, you're welcome for people who are thanking me. So I don't see any question. Or anybody raising their hands? I don't see that either. What? Okay. So there's nobody. And from the question side, I don't think let's change anything here. What? This is from the morning. Okay. Okay, so David, we can implement our last survey for this section.
Okay, let me launch it.
Yeah. In the meantime, type your questions while clicking on. Like I said, the first day, I don't like online. because I don't know what people are doing, what they're feeling. It's good. I would love. I prefer in-person interaction. So. Any other question? Come on, what is it? Question, said question. No? Okay. درجة يمنى أبابا. And why is this thing kind of dominated by East Africa? I see a lot of Ethiopian names. David, any reason? No? Okay. Baruch. Sheila. Okay, anyway, so I don't see any questions. So please, as you leave, please vote and then leave. You can leave once you voted. Unless you have a question. I think next 3 minutes will be good. If you have any question, yeah, I see a lot of thank yous. All very welcome. I mean, 200 would be very great. I mean, we'll have 200 people in a big auditorium and then look at your faces or look you playing on, I don't know, your phone or whatever. So out of 170 some people, we see. No, okay. I think there are some people who are doing their other business while this thing is on, but I'm fine. What forecasting? Clear. Wow. 68%. Moderate, okay. Easy. I like. But it's good. Normal understanding the forecast is not that easy, but I see that it's easy for the majority of the people. Okay, so David, we are done. Thank you very much, everybody. We'll see you tomorrow. Cannot see you, but at least we'll talk to you tomorrow.
Okay, thank you. Thank you.
See, I'm proving to be very formidable multilingual. At least I pretended to be, no? All right, okay, so let's stop here, David, and then if you can share these results will be great. I think they're similar. I'm happy that it is for the majority seem to be at least clear enough. Unclear, I see, 3% unclear, sorry, that's natural. All right, thank you very much and talk to you tomorrow.
Okay, thank you. Bye.